much, Joe. I don't feel credible as a machine learner and barely credible as a statistician. So, okay, thank you very much. So, Carl gave a great introduction this morning with lots of pictures and jokes, and now it's the Dow mathematician's turn to do lots of maths and equations and so on. But I'm very happy for this to become a discussion session, so any questions, please just stop me. Anything's unclear, you know, we can deviate from what I was planning. But the idea is to give a second introduction as if Carl Hendricks didn't happen, and just to take you through things in a different way as an introduction to GPs. Okay? So I think, embarrassingly, I've been giving this talk since 2016. And each year, I change a few things and add a few things. So the slides have bloated to beyond belief now. So we won't get through everything, but I'll kind of hop around depending on how the mood takes us. So I guess just to motivate things at the start, and just as an excuse to actually have some pretty pictures before we get going, I guess why are we interested in learning about GPs, about Gaussian processes? And I guess for most of us, the reason is because they've proven to be incredibly useful and effective in applied problems. Okay? I mean, not as headline-making as neural networks have been in the last few years, but Gaussian processes have seeped into all kind of different domain areas. So this bottom picture here is taken from the Pratt & Whitney website. So over a decade ago now, almost 2 decades ago, they decided to redesign their entire engineering process to incorporate uncertainty at every stage. And the key part of how they were doing that was based around this idea of Gaussian processes to keep the cost down. Okay. There's other examples here. So a lot of the work I do is on cardiac modelling. So patients are being treated for various different cardiac diseases, and we have expensive models we can build of these processes, but these models are too expensive for us to interrogate fully. And so one of the things we try and do is use Gaussian processes to help us explore this model space. Okay, it's kind of a lot of the way in which they're used in the world I work in, at least. Okay. So I thought what we'd do is start just by talking about Gaussian distributions, and then we'll move to Gaussian processes, and then I'll give you 3 or 4 different reasons why Gaussian processes are widely used, why they are kind of become ubiquitous in statistics and machine learning as a model of functions, as a probabilistic model of functions. Okay? And then just finally at the end, I'll talk about some of the difficulties of using Gaussian processes, what the things we hate about them and don't talk about enough, okay? But things that make life difficult. And you'll discover lots of these things as we do the workshops this afternoon. So you've all seen this before. This is not new to anyone. This is the Gaussian distribution. Okay? And just kind of the key things to note about this are that it's parameterized by 2 parameters, right? We've got a mean, mu, and a variance, sigma squared. And once we know those 2 things, you know everything there is to know about a particular Gaussian distribution. And the same thing is going to be true of Gaussian processes. We have to specify a mean and a variance. Okay. So why are Gaussians used everywhere? Okay, well, it's because they have all these nice properties, and well, you know, one of which is that they are easy to work with mathematically. Okay. So one of the key properties we're going to rely upon is that the family of Gaussians is what we're going to call closed under various different linear operations. In other words, you can do stuff to Gaussians, and quite often it remains Gaussian. So anything linear you do to it, you're going to end up with a different Gaussian. And the same is going to be true for Gaussian processes. Okay. We've got central limit theorem, of course, so they're kind of natural in that sense. When you've got a sum of a load of random stuff, it tends to quickly start looking Gaussian. Okay. There's other properties you might not have seen before, like this maximum entropy idea. So if you think about any distribution with a fixed mean and a fixed variance, you could then think about, well, what is the most uncertain distribution I could think of? And if we measure uncertainty by entropy, what's the most uncertain distribution that has that mean and variance? It turns out to be Gaussian. Okay? So one kind of sub-branch of machine learning or statistics is this max ent field, max entropy field, and their guiding belief is that you should model things with distributions that have the maximum entropy, and that's where the Gaussian appears. Yeah.
What differs the maximum entropy and maximum likelihood?
Oh, maximum likelihood is a method of estimation. So the likelihood function is a way we use to model the data. Okay, and if you've got unknown parameters, we might estimate them by maximizing the likelihood. This is nothing to do with estimation or inference. This is just saying entropy, which is a measure of disorder or uncertainty. Okay, if you had any distribution, what's the with a fixed mean and variance, what's the most uncertain distribution you could pick? Or the one with the highest entropy, it's this Gaussian. So it's not really related to likelihood, if that makes sense. Okay. They're infinitely divisible, these nice properties that we get that mathematicians care about. And the final one here is that anytime you have a procedure that involves squared error, squared loss function, so you look up the errors, you square them, you add them all up. So it's a common way of measuring an error or a loss, okay? Essentially, underneath the hood somewhere, you could formulate this as a probability model with a Gaussian distribution. So essentially, a squared loss, if you ever see that, is essentially going to be equivalent somewhere to having a Gaussian distribution. Okay. So there's all these kind of ways that these things arise naturally, and they kind of carry us across to the Gaussian process case. Okay. So if we think about multivariate Gaussian distributions for a moment, so that's where we've got two or more random variables. We've got exactly the same thing. All we need to do to specify a multivariate distribution is to specify its mean and its variance. But the mean now is a vector, and its variance is a matrix, okay, which I've called mu and sigma here. Okay. So if we had a two-dimensional bivariate Gaussian distribution, the mean is a vector with two numbers in, a mean for the first variable, y1, a mean for the second one, y2. Okay. A variance matrix, and the diagonal elements here are the variance of y1 and y2. And the cross terms, which I've called rho, sigma 1, sigma 2 here, are the covariance between these two variables. Yeah, please.
When deriving this form, it's quite difficult to start from the point to get understand the independent random variables and reparameterize them with respect to y. My question was, normally that's quite a cumbersome process to do that by hand. Is there a more elegant way to do that proof to get this form?
To get the PDF at the bottom?
Yeah, from like standard rules.
There probably is a more elegant way using moment-generating functions or something like that, but it's not too bad if you just do it by hand with a change of variables formula. But I agree, it's a few lines of algebra. But yes, the other way of doing it is just starting with this as the definition. Right? But yeah, good question, but I don't know off the top of my head a particularly elegant way. Okay. Certainly not an elementary elegant way. Okay. So let's just have a look at some pictures. So this is a cloud of samples. So I know Carl Henrik touched on this, okay, with two random variables, y1 and y2, with the mean of each of them 0, and they're independent here. They've got variance 1, and the correlation between them is 0. And for Gaussians, uncorrelated implies independence. That's the only distribution for which that's true. Okay? So we get this cloud of points that looks like a circle here. And if we look at the marginals, so we just ignore all the y2 values and just plot them on the y1 axis, you get this histogram that just looks like a univariate Gaussian. Okay, so it's that marginalization that Carl talked about, Carl Henrik talked about. Okay, yeah, I said all that. Okay. So we can do things. So we can change the mean. Okay, we can change the variance. So here I've just changed the mean to 0, 1, so it's shifted the cloud of points up, so its centre's moved. Okay, and I've made the variance of y2 smaller. It's now shrunk to 0.2, so we get an ellipse. It's not forming circles here, they're ellipses now. Okay. We can add correlations as well. So I've made the two variables correlated here, correlation of 0.9, and now you can see that there's information that we could learn about one variable from the other. So if now I came along and told you that y1 had a value of -2, you would know something about y2. Yeah? You know that y2 is probably around -2 as well. Okay. So knowing one variable tells you something about the other. And that wasn't true in the previous plot. If I told you something about y1 here, you'd learn nothing about y2. So it's this correlation that's allowed us to learn about one variable from another. Okay. The marginals haven't changed here at all. They're still both normal 0, 1 random variables, but now they're highly correlated. Okay. We can make the correlation stronger as well. Okay. Have I got a plot of that? Yeah, okay. So I've got a plot of that here. So I made the correlation 0.99, and now you're really starting to know a lot about one variable if I tell you the value of the other one. Okay, so if I tell you y1 now, you really can pin down y2 quite carefully. And so one of the things we can think about is the conditional distributions here. So if I came along and told you that y2 had the value of 1, that's where that line is across here, what does that tell us about y1? What can we say as a result of that? Okay, and what we're going to see is that there's a simple formula that tells us how the distribution of y1 has changed now that we know y2. Okay. y1 was normal 0, 1, remember, before we knew anything, but now once we observe that y2 takes the value of 1, it now has a mean of 0.9 and a smaller variance. Okay. So that's the kind of reasoning we're going to rely upon with Gaussian processes. We're going to do this in an infinite dimensional way rather than this kind of finite dimensional setting. Okay. So how do we get to infinite dimensions? There's different ways of doing this, but let's try it this way. Okay, so it's hard to visualize. Here I've got two variables, right? I've got a two-dimensional plot. I could probably do three-dimensional, but by the time I get to 10-dimensional, I can't plot them like this. So what I'm going to do instead is stack them next to each other. So the plot on the left is what we had a minute ago, a scatter plot of y1 and y2. What I'm doing now on the right is I've put an index on the x-axis here, and then I've joined the points up. So at index 1, I've got the value of y1, and at index 2, I've got the value of y2. I've joined them with a line so you can see which pairs of points go together. So that blue point in the bottom left corner is the line at the bottom down here. Okay. And once I've done this, I can start adding more variables. Okay. So here I've got 5 dimensions. So I've got a 5-dimensional multivariate Gaussian distribution, and I've set the mean vector to be 0, and I've given this to be the covariance matrix. So they all have variance 1, okay? And then we've got these covariances which decrease. Okay? So now I've got 5 indexes on the x-axis here, and each point, each sample from my 5-dimensional Gaussian distribution is a 5-dimensional object. Okay? So we've got 5 points on this line, and I've joined them together. Okay? And we can keep going. Okay? So this is 50 dimensions. I've just got 50 indices now along the x-axis. Okay? And each line here has 50 points on it. So is one realization of my 50-dimensional Gaussian distribution. 1 point for my Gaussian distribution. Okay. And that's going to lead us to Gaussian processes. So we can basically think of Gaussian processes as being an infinite dimensional distribution where our index set, instead of having just 50 points, so I've got 40 points here, haven't I? I've got an infinite number of index locations. Okay, so it could be the real line. Yeah, a function is something like this, right? Given an x, it tells you what y is. Okay. So you've got an index x, and that tells you what the y is, and that's how we're going to think about as Gaussian processes. Okay. We're going to think about them as functions where our x is our index to tell us which random variable we're referring to. Given an x, there's a random variable associated to it. We're going to pick that. Okay. Okay. So to do it a bit more carefully, the way mathematicians define stochastic processes is just as a collection of random variables, okay, indexed by some variable. So x is going to be my index, and y is a collection of random variables where for each x, there's a different value of y of x, a random variable. Okay? And x just tells me which of those random variables I want to select. It's my index. Okay? So usually we have y of x being a real number, and x, the set of possible inputs, might be a subset of real space, Euclidean space. So typically, in those plots, it was just like the real line, right? Okay, so we can think of this as a function, yeah, of x. Y is a function of x, or you can think of it as a collection of random variables, however you prefer. So that's stochastic processes. Okay. If we've got an infinite index set, for example, if our index set is the real line, there's an infinite number of indices in there, then we have an infinite dimensional stochastic process. Yeah, there's an infinite number of random variables in our process. So what Kolmogorov showed was that in order to understand stochastic processes, okay, in order to understand their distribution, it's enough just to be able to understand their finite dimensional distributions. Okay, so what does that mean? It means if we pick any finite collection of random variables from our stochastic process, so let's suppose I pick out n indices, x1, x2, up to xn. I've just picked out n different random variables. If I can write down the law of them, the distribution of them, yep, this thing, then if I can do that for any finite set of random variables, I've specified my stochastic process. That's all I need to do to specify fully the stochastic process, is to specify its finite dimensional distributions. Okay. There's some rules you have to follow to make sure that is you end up with a real process, something that makes sense. That's fine. So what's a Gaussian process? Well, it's just a stochastic process where all the finite dimensional distributions are Gaussian. So in other words, if I pick out any finite set of random variables for my process, then that has a Gaussian distribution. Okay, that's it. Yeah? Just if we think of any finite subset of the random variables, they are Gaussian, okay, with some mean and some variance. Okay. And that is our definition here of a Gaussian process. And because we said that Gaussian distributions are easy to work with, it means Gaussian processes are easy to work with. Okay. That doesn't mean they're not hugely complicated and going to cause you lots of headaches and take you a long time to learn how to use and so on. But what I mean is there are almost no other stochastic processes that are as easy to understand. There's Poisson processes and Gaussian processes, and then everything else is a nightmare. Okay? They are the two kind of main stochastic processes that probabilists know and understand completely, essentially. Okay? Okay, what I'm going to write here, I'm going to write things like y, and I'm going to often put this brackets with a dot in to indicate it's a function of something. Okay, I'm going to write y twiddles GP to indicate that it's a random variable and it has a distribution that is a Gaussian process. Okay, and we'll dig more into that. Okay, so it's a y is a function, and we're going to model it as a Gaussian process. Okay. So for Gaussian distributions, we said we only need the mean vector, or scalar, and the covariance matrix. The same is true for Gaussian processes, but now because they're functions, we need to specify a mean function and a covariance function, okay, that work for any of our index sets. Okay. So to flesh out that notation, I'll often write things like, you see people write things like this. Y, as a function of something, is modelled as a Gaussian process that has a mean function m and a covariance function k. Okay. And that's just how we specify what the model is. It's the equivalent of writing this for Gaussian distributions. We write this for Gaussian processes. Okay. And our job then, as a modeler, is to pick m and to pick k. And that's it, basically. The rest then kind of follows from the maths. Okay, so yeah, just to specify what they are. The mean function n is the expected value of y at a given index. So if you pick out a random variable y of x, its expected value is m of x. And if you pick out two variables, so y at x and y at x prime, then the covariance between them is k of x and x prime. Okay? So that tells us the mean and variance and covariance. Yeah, yeah, please.
Sorry, the previous slide. Can you please repeat what is the Gaussian distribution? We have the probability. It is equal to what?
Say that again, sorry.
It is equal to something because it just says that for all x months and x n probability, then shouldn't it equal to something? Or
So Kolmogorov's theorem says that if you can specify this, you've specified the law of the process. Yep. For a Gaussian process, these are Gaussian distributed. I mean, so we can't write down this expression here in closed form for Gaussians because the CDF of a Gaussian isn't known. Okay, but we know what it is. We just can't write it down mathematically. Okay, so there's some technicalities here. Right? This is specifying its distribution, from which many distributions admit a density. Okay, and for Gaussians we have a density. Okay, so there's some technicalities I've smudged over. Okay, but basically for a Gaussian process we know the finite dimensional distributions. Does that answer your question? Okay, come on, talk to me at lunchtime if not, okay, or in the workshop. Okay, so there's some rules you have to follow, okay, about picking these mean and covariance functions. So the mean function, we can do whatever we like, okay, no rules. You can pick whatever you want for the mean function. Okay? We've got to be able to work with it and so on, but it's fine. The covariance function is more difficult, okay. We have to, as Carl Henry says, pick positive, definite covariance functions. Okay. So often what we do is we use covariance functions that are a function of the index locations. So we say the covariance between y of x and y of x prime is a function of x and x prime. And there's some technical kind of criteria. It's got to lead to what's called a positive semi-definite function. Okay. Or what that means is, if I give you any n locations, if I pick out x1, xn, and I form the n by n covariance matrix, this matrix, that's got to be a variance matrix. Yeah, it can't have negatives on the diagonal. You can't have negative variances, for example. Yeah? So this has got to be a positive semi-definite matrix. Yeah?
What's the gram matrix mean?
Sorry, a gram matrix is just what some mathematicians or and machine learners often call this matrix. Okay?
Just any matrix that's positive,
I think the way they use it is it's a matrix formed of inner products between points, which won't make sense to you yet, because I've not told you these are inner products, but essentially it's a matrix formed of inner products. Okay? Sorry, covariance matrix. Yep. Yeah, sorry, I should have done that. So these have just got to be valid variances, basically. You can't have invalid variance matrices. This turns out to be quite a difficult condition to work with. It's quite hard to create these functions. And so what we tend to do is work with the kind of a library of covariance functions, and we pick from that library, okay, a small number of choices, and we try and combine them in interesting ways that I'll try and illustrate. Okay. So just some jargon you need to know. Okay. So often we assume that k is only a function of the distance between the locations. So in other words, the covariance between y at x and y at x prime is just a function of the distance between x and x prime. Okay. And that's what's called a stationary process. Why stationary? Well, if you were to translate it along the x-axis, things don't really change in distribution. Okay? It looks the same between 1 and 2 in distribution as it does between 2 and 3. It doesn't matter. It's a stationary process. We also have what's called isotropic functions. If x is a vector valued, or even if not, okay, if the covariance only depends on the modulus of the distance between x and x prime, then we said it's isotropic. That just means it's the same in all directions. So the if your input space is an area, and you're modelling weather over the country, say, temperature over the country as a function of location, if it's an isotropic covariance function, it means it's the same pointing north-south as it does east-west.
Do you mean, so that, sorry, that's L2 norm, is it?
Yeah, pick your favourite norm, but yeah.
Oh, but just some norm.
Some norm, okay. Yeah. But L2, yeah. Okay, so the key thing about Gaussian processes then is this choice of the covariance function, k. And it's this choice of k that really determines the nature of the GP, the flavour of the GP. Okay? When we pick k, what we're implicitly doing is picking a space of functions we're considering. Okay? And what k we choose determines what that space of functions looks like. Okay, so I said that. We normally pick k by picking from a small candidate set, so let's just look at some of those candidate sets. Okay. So this is one choice, one valid choice of k. Okay. So it's the difference between x and x prime squared, e to the power of negative of that. Okay. So this has got various different names. It's sometimes called an RBF kernel, a radial basis function kernel. Sometimes called squared exponential, or sometimes exponentiated quadratic. Okay. Some misguided people call it a Gaussian kernel. Okay, it looks like a Gaussian PDF. Okay. It's, probably the most popular choice is something like this. So what I've plotted here then are different random samples from a Gaussian process with this covariance function and zero mean. Okay? So each line here is one function, and it's one sample from my Gaussian process. Okay? So along one of these lines, there's an infinite number of values. Yeah, because my index set here is infinite, but each line is one sample. Okay. And we can change things about this covariance function. So often you see a number in the denominator here, okay? And this is called, we'll get into this more in the lab later, this is the length scale of the process. This tells us how quickly this function wobbles up and down, basically. How quickly it can change, how quickly the correlation drops off. Okay? So if I make that number smaller, the process wiggles more. If I make it bigger, so I've gone from a quarter to 4, okay, it varies slower. You know, the functions vary much more slowly. So that's the length scale. We can also change the number out the front here. So I've put a number 100 at the front here, and all that's done is change my y-axis. Samples were varying between 3 and -3 in all these plots. Now I've multiplied by 100, I've changed the variance, I've made the variance process 100, so the samples now vary between 30 and -30, roughly speaking. Okay. So in general, you often see this covariance function parameterized in this way. So we often have 2 free parameters in it, a variance parameter up front and a length scale parameter in here. And what we might often do is try and estimate these parameters from the data in some way. Yep. So we'd pick this as a family of covariance functions, would use the RBF kernel, RBF covariance function, and then we would estimate these 2 parameters, lambda and tau. Okay. Yeah, please.
What's the reason behind parameterizing the square?
Because negative values don't make sense, basically. Yeah, that's it. They've got to be positive. It just makes that happen. So this is just one choice of kernel. and functions, samples from this kernel are incredibly smooth. Okay? They can wobble up and down slowly or quickly, but all of these lines here are differentiable. They're twice differentiable, 3 times differentiable. They're infinitely differentiable. They're analytic functions. Okay? That makes them incredibly smooth. They have derivatives of all orders. Okay? So this leads to lots of kind of weird facts. So if you were to know the value of this function at a point, and the value of all its derivatives at that point, but that for analytic functions is the same as knowing the function everywhere. Okay? So there's kind of weird consequences of this. So for that reason, a lot of people kind of argue this isn't a good choice. But as I say, it's still the most commonly used choice. Okay. What other examples are there? There's a family of covariance functions called the return covariance functions. And these covariance functions get indexed by their degrees of freedom. Okay. So this is the return 3/2 kernel here. Okay. So you normally see it as fractional powers of 2. So you get return 1/2, return 3/2, and 5/2 are the ones people tend to use. Okay. And why do we like these? It's because this degree of freedom controls how many times these samples are differentiable. Okay. So we have that from return 3/2 produces functions that are 1 time differentiable. So you can differentiate each of these curves once, but not twice. Okay? So that makes them rougher, if you like, than the RBF. They're not as smooth. They don't have all derivatives. You can only differentiate 1 time. Return 5/2, you can differentiate 2 times as 2 derivatives, first and second derivative. Return 7/2 is 3 derivatives, and so on. Okay? By the time you get to 7/2, having 3 derivatives, it essentially looks, by eye, the same as an RBF kernel. Okay, so that's why people tend not to consider it. They tend to consider 3/2 and 5/2. Okay. There's also 1/2, which is called the exponential kernel, and that is 1 time differentiable. Okay. So you'll see these things in the workshops this afternoon, where you'll try them out on a data set. But there are also lots of other weird and wonderful kernels we can use. Okay, so this is a Brownian motion kernel. Okay. So Brownian motion is a continuous, leads to continuous sample paths, almost everywhere continuous, but almost nowhere differentiable. So these functions aren't differentiable anywhere. Okay. And if you've done any kind of basic analysis course, you've probably studied Brownian motion before, but they're just another example of a Gaussian process. Okay. So these are actually infinitely variable, so that means you can pick any segment you like of any one of these curves, arbitrarily small, and if you zoomed in enough, you would find the complete works of Shakespeare written in your own handwriting, if you looked hard enough. Yeah? There's infinite variation, unbounded variation. Okay, so you can find any pattern you like in these things if you look hard enough.
Does that also work for fractal functions?
I don't know. You have to ask a real mathematician, but might possibly. Yeah. Okay. Anything that's infinitely variable, yeah. Okay, so this is the white noise kernel. Okay. So this says that the covariance between x at x and x prime is 1 if x equals x prime and 0 otherwise. And so in other words, this is just a collection, an infinite collection of independent random variables. Yeah? So there's no relationship. If I told you the value at 1, it would tell you nothing about the value of the function anywhere else. It's just white noise. Okay? And in some sense, it's the derivative of the Brownian motion kernel. Okay. Okay, so one final kind of example to try and understand what's happening a little bit here. So let's consider the kernel that is x times x prime. Okay. And these are random samples from that kernel. And you can see they are just straight lines going through the origin. Okay. So let's see if we can understand what's happening here a little bit. Okay. So let's think about a model of functions. Okay. And what we're going to show is that this model of functions leads to this covariance function. So let's consider functions of the form y of x is c times x. Okay, so just straight lines through the origin, where let c be a random variable, just a scalar, with a normal 0-1 distribution. Okay. Then if we think about the covariance for this function, so if we can think about the covariance between y at x and y at x prime, that's the covariance between c of x and c of x prime. Well, x and x prime aren't random, they're just indexes. So this is x times the covariance of c with itself, or its variance, in other words, times x prime. And the variance of c is 1. Okay, so we get the covariance here is x prime, which is what we started with. Okay, so that's why, for this, which is called a linear kernel quite often, this corresponds to straight lines through the origin. Okay, and the distribution of the gradient is controlled, in this case, by the distribution we assume here. Okay. So what we've shown in this little calculation here is that y of x is a Gaussian process. I mean, we've not done all the work, but if c is Gaussian, y of x is Gaussian. Its mean must be 0 because the mean of c is 0. So this is a GP with mean 0 and this covariance function. Okay. Yeah?
Is there a direct relationship between the differentiability of the kernel and differentiability of the GP sample?
Yeah, absolutely. Okay. I think I've even got a slide somewhere, so let's skip to it. Okay. So the properties of your function, of your GP, are inherited from K here, and you can stare all you like at these covariance functions, and it doesn't, well, for me anyway, it doesn't give me any insight at all as to what the samples are going to look like. You know, it makes no sense to me staring that that's going to be straight lines, and that's going to be Woods differentiable functions, and that's analytic functions. You know, you can stare at these covariance functions, and it doesn't help. But mathematically, we understand how the properties flow from one to the other. Okay? So f of x is going to be a continuous function at x if and only if the mean function m is continuous at x star and if the covariance function is continuous at x star. Okay? So, or for stationary kernels, okay, what we require is that it's continuous at 0. Yep. So if the covariance function is continuous at 0, the random samples will be continuous. If it's differentiable at 0, the random samples will be differentiable. If it's twice differentiable, the random samples will be twice differentiable, and so on. Okay? So for stationary kernels, we just have to check the properties of K at 0. Okay? All of this, of course, is complicated because we've got random things. So it's not the definition of continuity that you learnt in your first analysis course. It's what's called mean square continuity. So we've got expectations all over the place that make this horrible to work with, but it's the definition we've got. Okay.
Sorry, so this isn't the epsilon delta definition.
Well, it is, but in this sense. Okay. So if that goes to 0. Okay, so you have the same thing. If given a delta, given an epsilon, there is a delta for which that is less than epsilon. So it is, but you've got to work with that rather than the norm between f of x and f of x star. Yeah. Okay. Yeah.
It might be hypothetical, but is that the only sense of continuous?
Again, I'm on shaky grounds. I'm not really a probabilist, but no, there are other senses in which we could consider continuity. Okay, but I don't know what they are, but I know they exist. Okay. Yeah, Carl Henrik said that, so I'm going to skip that. Just to say, we've got a small family of covariance functions, some of the ones I've mentioned here, plus a few others, and then we can do things to them to create new covariances. You can add covariance functions together, and it's still a covariance function. You can multiply them together, it's still a covariance function. You can warp them in various ways, okay, which you'll see later. Okay? So there's things you can do to covariance functions that lead to other covariance functions, but our starting block our starting set of covariance functions we consider is quite small. Okay. Yeah, so just to say then, these covariance functions we pick often have 3 parameters in them. We often call them hyperparameters. So before we saw the length scale parameter and a variance parameter. Okay. So we talked about what they did, and typically what we do is, you pick your favourite method for estimating parameters, and you use that to learn these length scale parameters. Okay. The easiest thing that most of us do most of the time is use maximum likelihood estimation to pick a good length scale and a good variance. Okay? And there's things that can go wrong in that, which you'll discover later. But you can be Bayesian about it. You can do it by cross-validation, however you like. Okay? We just need some way of picking these things. Okay. Any questions at this point? Yeah, please. Say it again, sorry.
What is the properties of a covariance function? What does it mean to hold?
So it's got to be what's called positive semi-definite. So, I don't know if there's a pen. So for a matrix, so, if this is a n by n matrix, it just means you've got to have x transposed ax being bigger than or equal to 0 for all possible vectors x. And you've got a similar definition for positive semi-definite functions, okay? But basically, it just needs to lead to variance matrices that have this property. Yeah? Yeah, please.
How do I know that a family of coordinates is working for my data?
So, really good question. So, what we tend to do is a bit of trial and error. So, you might start with RBF, say, and then you'd estimate the hyperparameters using maximum likelihood, and then you'd do some sort of empirical test of its skill of that model. So, one thing you can do is cross-validation. Yeah? Fit to some data, predict other data that the model hasn't seen yet. Yeah? And if it predicts well, you've got a good covariance function. Or if you've got two covariance, you want to compare Matern and RBF, you could try both and see which predicts best. Yeah? Or there's other things you can do. You can look at the marginalized likelihood, which is a score that you can use. There's a whole, every method you know about for picking between doing model selection applies here. Pick your favorite method. Mine is predictive skill, like cross-validation. Yeah. The one there, and then there. Yeah, please.
Yeah. So I wanted to confirm. So basically, what we want to estimate is the scaling parameter on the covariance function. So
Yeah.
we plug it, we use it into to predict y and then calculate the loss and then backpropagate to differentiate it and then update the the tau and lambda.
That's exactly what we do. Yeah.
So it's all for every kernel that we will use.
Yeah, for nearly every kernel you use will have some free parameters, okay? And it's the same procedure for estimating those hyperparameters in each case. Typically, you look at the log likelihood, and then you optimize it. Okay? And nearly all software you use will have that built in for you. So when we look, I don't know what software is being used this year, Maurizio. Is it GPy or GPyTorch? GPy, okay. So you pick a covariance function, family, RBF, say. You say what your model is, so I want to model y as a Gaussian process with that covariance function. Then you have an optimize command, and that optimize command estimates the hyperparameters by a maximum likelihood with a particular optimizer, and then you test the model. Yeah? So it's always the same kind of procedure. Compute a score, log likelihood, typically optimize it. Yeah.
Maybe one last question.
Yeah, please.
So are the parameters we want to estimate just a single value or maybe like multiple values based on the observation
So what I've presented here would just be a single value, but you can make the likelihood functions as complex and weird and wonderful as you like, as long as it is valid. Okay? And so, you know, people do all sorts of things to make them more interesting and have them varying. But yeah, for here it's just a number, just a scalar. Okay? There's a question down here. Yeah, please.
Yeah, kind of building off that, I'm thinking about these different kernels that you mentioned and also how they could be combined and
Yeah.
result in other covariance functions. As far as you know, is there a major difference in the compute needs or just what actually happens on a computer when you're doing this, and if that should or shouldn't factor into
So mathematically, there's no difference. Okay, they all lead to an n by n matrix if you've got n data points, and you've got to invert that matrix somehow. Okay, solve some linear system that's that big. In practice, some of the covariance functions lead to numerical difficulties. In particular, that n by n matrix has a poor condition number. It's close to not invertible. Okay? And so, for example, the RBF kernel is particularly prone to that. Okay? So RBF often leads to numerical instabilities that we have various ways to get around, which I'll talk about in a moment. Okay? And so for that reason, you know, Matern is often a better choice because it leads to better condition number of the covariance matrix. Yeah. Yeah, good question. Right, over here.
Could you explain a little bit more why the covariance matrix needs to be consistent?
Why? Just because I've got it somewhere here. Okay. Okay. So, you know, if I pick out the value of my function at a number of locations, it's saying that we need that object, that vector of n points, to have a Gaussian distribution. Okay? And that Gaussian distribution has a covariance matrix, and variance matrices have to be positive definite, or they're not variances. So that's why. Yeah? Yeah, good question.
Sorry if I missed it, but I'm wondering why we're interested specifically in mean square continuity and differentiability.
I'm not sure we are particularly interested in them. It's just they're what we know how to work with mathematically. Okay? So they are the types of continuity that the probabilists understand for stochastic processes. There are probably others. I don't know about them. Okay? But they're harder to work with. They're the easiest forms of continuity to work with. Okay? Yeah.
So I'd have to choose the likelihood function as well. So that means there's some contribution not happening. So is there any thumb rule I can use to pick out a family of likelihood function for a particular kernel?
Well, so the likelihood function here is always going to be Gaussian. Okay? Because we're doing Gaussian processes, that's the probability of my, you know, the likelihood function is the probability of my data given my parameters, and that's always going to be Gaussian here. Okay. We can do non-Gaussian things with Gaussian processes, it turns out, but that's another talk, okay? Probably tomorrow, maybe. But for the purposes here, everything is Gaussian, so our likelihood function is just Gaussian. And all we have to choose is the covariance function. Okay. Great. Okay. Good. So let's carry on then. So you know, why would you want to use this kind of very restricted class of models? And it's because they're easy to work with, okay? Easier than the alternatives. Okay? And the key one that we're interested in is that conditional distributions are still Gaussian. Okay? If you've got a multivariate Gaussian or a Gaussian process and you observe something about it, everything is still Gaussian. So Carl Henrik said it's worthwhile once in your life going through this calculation, so I'm going to sketch it out now, okay? But it's still worth you doing it, but this is roughly how it goes. So just in the Gaussian setting, Gaussian distribution setting, let's suppose we have a random variable, and I'll split it with two bivariate variables, so it's got two elements in it, with this mean vector and this covariance matrix. And then what we're going to show is that if you're to observe y1, so the first element here, that y2 still has a Gaussian distribution, but we've got a new mean vector and a new covariance, a new variance. Okay? So that's what we're going to show. And why is this useful? It's saying that, you know, once I've got this process, if I observe something, I get the same process back again. Everything remains Gaussian. And the way I compute it is just linear algebra. Okay, these are scalars here, but they're going to be vectors and matrices in a minute. It's just matrix multiplication, all it is, and solving a linear system, an inverse. Okay. So why is this true? So just a very brief kind of sketch of it. What we want to think about here is the distribution of y2 if we're told y1. Okay? So if you've seen this calculation before, you know how these kind of things go. What we've got to do is just think about, sketch out what this shape looks like, and then think, does that correspond to anything I recognise? Okay? So we're only caring about y2 varying, so this, as a function of y2, is just proportional to this. Yep? y1 doesn't matter, but it's fixed. Okay? So if I write this out, I've done it in the vector form here, multivariate form here. This is the PDF of the multivariate PDF, okay? And if I was to spell that a little bit more, this is this vector on our y minus its mean vector, transpose, times this matrix, which I've said is the inverse of my covariance matrix, okay, times this term again. So it's a quadratic, yeah? And all we care about is what happens to y2 here. Okay? So if I expand this, you know, multiply out my brackets, essentially, what we get is something that is squared in y2. So I've got this bottom term, y2 minus mu2 times q22, times y2 minus mu2, plus the cross term, so I get a 2 with the y2 minus mu2, q21, y1 minus u1. Okay, so I've got a cross term, and then we've got another term with y1 in, and I don't care about that. That drops off my proportional sign because it's not got a y2 in it. And what's this? What's this the PDF of? Well, this is just e to the power of a quadratic. So it's still a Gaussian, right? That's the definition of a Gaussian. Okay? We started off with something e to the power of a quadratic. I've got rid of the y1 bits, I don't care. Okay? And it's still e to the power of something that's quadratic in my term. So this is still multivariate Gaussian. Okay? And a bit of kind of bookkeeping will kind of get you what you need then. You just collect the terms together. Okay? If you've done this kind of thing before, it'll seem completely familiar to you. If you haven't, go away and try it. It's worth doing it. It looks complicated, but it is literally just quadratics. Yeah, you're just collecting terms in quadratics. So how does this translate across to Gaussian processes? Okay. So this result is that if we observe y1, y2 is Gaussian with a new mean and new variance. Well, it's just exactly the same, but with functions. So let's suppose that we've got f is our GP, a Gaussian process, with mean function m, covariance matrix k. And we know that if we consider the value of this function at a finite set of points, so I've considered it at x1 up to xn, and at a generic point x, we know that has a Gaussian distribution with this mean vector, mu. Okay, so I've just put the means all together, and this covariance matrix, sigma. Okay. And I've colour-coded bits here just because I'm going to pull out these different bits of this matrix. Okay. I've got this red bit here that is the covariance between all these x's that have a number attached to them. These are the bits where I'm going to observe my function. Okay. And then I've got the covariances between my generic input x, okay, and the x's with the index on. Okay. What's going to be in this blue bit here. And all we need to do then is, if we want to consider the distribution of f, if we were to observe f at these points, at x1 and xn, is to apply what we did a second ago in the distribution case. Okay? So using exactly the same formulas I had a moment ago, we get that the distribution of f of x is normal, and its mean is this thing, and its variance is this thing. Okay? where those colour codes correspond to the colours on the previous slide. Okay. So why is that useful? What we've said is that if we start out with f being a Gaussian process with some mean m and some covariance k, if we were to then observe f at a number of locations, f of x is still a Gaussian process. We've just modified the mean function. Okay? So m, our prime mean before, is replaced by m bar, and k is replaced by k bar. We've gone from one mean function to another mean function, one covariance function to another covariance function, prior to posterior. Okay? And all it is two little equations, yeah, with matrix, vector, multiplication. That's all we've had to do to work this out. Okay? Okay, I think that just summarises that. So these are the pictures that people normally show. Carl Henrik showed some of them. Okay. We start out with a prior belief about our function. These are random samples from our prior, okay, with some prior mean function, some prior covariance function. We observe the function somewhere. I'm not sure you can see those data points, but I've observed it at 5 points there. You see the lines converge. And what we get is a different Gaussian process with a different mean function and a different covariance function. And then, you can do the kind of plots that Carl Henrik hates, okay, at the end with the posterior mean and the posterior variance and so on. Okay. So you're going to generate these this afternoon and try this stuff out for yourself. Okay. Any questions at this point? It's kind of like yeah, please. Sorry, my hearing is really terrible. Say that again.
Just to confirm, there's no restriction that it has to be continuous random variable. It can still take discrete values, right?
Yeah. It doesn't have to be continuous at all. So this works. Your index set doesn't have to be continuous. It doesn't have to be a real line. It can be all sorts of weird and wonderful things. You can have jumps in these things. They can be nowhere continuous. It can be all kinds of weird and wonderful stuff. It's just in practice, we nearly always model in continuous stuff. And so we tend to have continuous mean functions and covariance functions, yeah.
Do you have a mix of the two? Could you have a joint PDF which is part discrete and part continuous?
Yeah, absolutely. So in lots of applications we've looked at, we have discontinuous processes. It's typically hard to learn where this discontinuity is, but if you know where it is, you can build it in. Okay.
Is there a way to learn that, not a priori, but during the process?
Yes, but again, it becomes really challenging, because if you could have jumps anywhere, all of a sudden, the easiest way to explain your data is just to put jumps everywhere. And so it's quite hard to have a model that kind of says, we have jumps, but not too many.
Is that where, like, something like a maximum posteriori would help?
Yeah, possibly. Okay. So there's lots of different approaches for doing things. But as Carl Henrik alluded to earlier, the more flexible your model is, the more data you need to pin it down. So imposing continuity is quite a strong assumption, and it really helps. If you don't have that assumption of continuity, where the hell do you start with modelling? It's really difficult. Okay. Yeah, please.
In all these graphs so far, when you have data, you essentially are saying that your uncertainty is 0 at every data point.
Yeah.
But for any real-world measurements, you're going to have your data points are themselves going to be like Gaussian.
Absolutely.
So is that like a trivial extension to this? If you have
Yeah. Good question. Okay. So what we're normally doing is interpolation here. As you say, we're going through the data points exactly. In real life, we don't normally observe the function exactly. We've observed it with noise. So let's suppose we've observed it with Gaussian noise, zero mean Gaussian noise. Okay. How is that going to change our calculations? All that does is when we think about the covariance matrix of y1 to yn now with f, if we get exactly the same as before, but instead of just having this kxx term in here, we get this extra bit due to our observation error. Because we've got, we noisily observed y at each location. Okay? So nothing else changes. The mass remains exactly as it was before. It's just we replace kxx by this noisy bit in the middle. Okay? And what that does is mean that we no longer interpolate the data points. Okay? Now, the uncertainty shrinks near the data points. So, here the uncertainty is smaller than in places where we have no data. But because we've said our measurements are noisy, unless we have repeat measurements in a place, we're never going to tie down that uncertainty. Okay? Of course, here we've introduced a new parameter that we might want to estimate, the measurement error. And if that parameter gets smaller, our uncertainty shrinks. We get closer back to interpolation, the closer it gets to 0. But we can just add it to our list of parameters with the length scale and the variance and estimate it, if we like. Okay.
So what do you mean by nuggets?
Yeah, thanks. Gaussian process, well, there's a branch of spatial statistics called Kriging, okay, that I think started being developed in the 60s with Krieger and Matheron, and they had their own language, okay, and it wasn't until, I think, the late 70s we realised they're essentially the same as Gaussian processes in some way, and so in some of the statistics we still use some of that language. So the nugget is what the language of that community to say there's noise around a point. We would say observation error in machine learning, I guess, but it's often called a nugget in the Gaussian process community. It's the variance at a point. Okay. Yeah, please.
Would you run into identifiability issues when you model that into your whole
Absolutely, yeah. Horrible identifiability issues.
Would it be better off if we do something like MLE, empirical variance first? You use that and then try everything else?
There are multiple different strategies people use. And I'll just skip ahead to that example now because I think it's informative. Okay, we'll come back if we have time to some of this other stuff. But even with no nugget term, we have problems with these hyperparameters. Okay, so a Gaussian process is a very complex object. It's infinite dimensional. Okay. And what we find is that even mathematically, asymptotically, if we have infinite amounts of data, there are situations we can't identify some of the parameters. Okay? So, for example, I like this example. If you have a Gaussian process on 0, 1, okay, and you have this exponential covariance function, asymptotically, as we have more and more data between 0 and 1, you can't identify the length scale, it's 1 over the length scale here, isn't it, kappa, and the variance sigma squared. Okay? You can only identify the product of them. Okay? So even in the best case, there are non-identifiabilities, and as soon as you add nugget terms, variance, observation error, it gets much worse. Okay? So hyperparameter estimation is a bit of a nightmare in Gaussian processes. It's one of the kind of the key headaches we have, as you'll see today. So one, that likelihood surface isn't always very informative. Okay? It can have multiple minima or maxima, whatever. It's often very flat. But sometimes our optimizers just fail. So I use this example from GPy. So here I've got, 10 data points that come from a sine wave. Okay? And what you want your model to do is to learn that it's a sine wave. But I found in GPy, and any software, about 1 time in 10, when you run your optimizer, you'll end up with a surface like this. So this Gaussian process says the mean of the data is 0, there's no correlation anywhere, it's all just observation error. Okay? And that's almost as good an explanation for these data as this model here. Yeah? So if you look at the maximized likelihoods, they're very close to each other. And about 1 time in 10, the optimizer gets stuck here rather than here. Yeah? So, yes, to answer your question, that there are a ton of identifiability issues, and we have various workarounds to these, the one you suggest, but often simpler things, just running the optimizer multiple times and seeing which fits best, yeah? Or which we like the look of best. Okay. We often use prior distributions. So in this case, the measurement error has been estimated to be 1 here. So in this case, I might put a strong prior on my measurement error and say, I think it's small, 0.1. And that would probably force me into the solution on the right. Yeah?
How do you know if the problem arises from like stuck at local model with optimizer or numerical instability of your inverse matrix?
Very difficult. Very difficult. So one-dimensional, we can plot things. If you've got a GP with a 10-dimensional input, it's a lot of trial and error, testing, running it multiple times, seeing if you get better fits. There's. So jitter is another one. So jitter is another bit of jargon. It's essentially a nugget term, an observation error, but used just for the numerical convenience. Okay. So there's all these kind of tricks that people use to make them work, and hopefully most of the time you don't run into these problems, but sometimes you do. Yeah. Yeah. Yeah, so this is exactly Carl Henrich's point, that it's better to plot the sample lines, rather than these plots that have ignored all that covariance. Absolutely, yeah. See, they were listening, Carl, which is good.
The reason why it's really bad, try and do it for a Bayesian neural network.
Yeah.
They hide the results by doing that plot, and it looks like it makes sense, but your samples look goofy.
Yeah, I mean, at least with GPs, we know mathematically how the samples kind of behave. With a complex neural network, you have no idea, no understanding, in most cases, what they really look like. Okay, any other questions here? Okay, so let me just pick off some of these other topics. I told you I have a million slides here, never get through them. Yeah, let's just mention that. So just before we kind of talk about the advantages of them, there are various additional tricks that are used commonly in statistics and less commonly in machine learning for whatever reason. Okay. So one is, if we have a mean function that is itself a linear model, okay, that's often a sensible thing to do, to build in some kind of structure if you know it's there. Okay. In this case, where you've got this free parameter beta floating around, if you give beta a normal prior, everything integrates out. You get what's called a conjugate analysis. You don't have to do any extra computation. It just drops out nicely mathematically. We still get a GP at the end. Okay, it's a slight modification to that M bar and K bar formula I gave you before. It's just an extra tweak to them. Similarly, there's some form of conjugate analysis available for the covariance functions. If your covariance function is some variance parameter times something, as it nearly always is, if you give sigma squared an inverse gamma prior, okay, then again you can integrate that out, and instead of a Gaussian process, you get a T process, okay, which aren't nearly as nice, but as long as your number of data points is large, it's essentially still a Gaussian process. Okay. There's not much difference. So just to say, there are some options for dealing with these hyperparameters in a Bayesian way. That doesn't mean you have to do MCMC. Okay. Other parameters, like the length scale parameter and the nugget parameter, are much harder to deal with, and we have to resort either to optimization, maximum likelihood, or MCMC if you want to take a Bayesian approach about them. Okay. So just to say, these methods are out there. Okay. So just to summarize then, I've got various answers for why you might want to use Gaussian processes, okay, why they're useful. So the first one we've seen is The first kind of reason is that you can do stuff to them mathematically, and it remains a nice family. So we've seen this property that they're what I've called here closed under Bayesian conditioning. So in other words, you can observe part of your process, and your function conditional on that is still a Gaussian process. We just changed the mean. So that's really nice. That's not true for any other process I can think of. Yep. They remain in the same family, which is nice. You could also do nice stuff to them, like add them together. Okay? And they're still Gaussian processes. So you'll see, is the more and lower data set still used, Maurizio? Is it? Yeah. So this afternoon, you'll see an example where you'll add lots of GPs to each other to make your modelling richer. Okay, and that's this kind of thing. And in real applications, this will be useful. And in general, they're close on any linear operation. Okay, so you can differentiate them, and the derivative process is a Gaussian process, which is nice. Yeah? So the kind of work Maurizio does is to use these in differential equations. You can push Gaussian processes through a differential equation, and it's still a Gaussian process. Yeah? So it gives us lots of nice options for doing detailed modelling, building in physics, and so on. You can integrate them, it's still Gaussian, so on. Okay? So we can do lots to them, and mathematically they remain the same. Okay, second reason. So this is really what Carl Henrik was talking about earlier. The GPs are kind of a non-parametric way of modelling the world. Okay? So if we just try and unpack that a little bit mathematically, what does that mean? Okay? So we've said this kind of K determines the space of functions that the sample paths, the samples live in. Okay? So let's suppose we're given some data like this. Okay. What we're going to try and show is that this is essentially like linear regression. Okay? So let's consider doing linear regression here. Okay? So we're going to model y as x beta and do this by minimizing the sum of squares. Okay? I don't want to let beta be too big, so I've regularized it here. So this is called ridge regression, or Tikhonov regularization, just least squares estimation, right, with a regularization term. So we know how to do this. Yeah, you almost certainly saw this in some sort of undergraduate course somewhere. Okay? We know the formula for this. The best value of beta hat, is given by this. Yep. Well, we can actually rewrite this a little bit. Okay? So I mean, I've put the details in here, but look at them later. Okay? An equivalent way of doing this is to get exactly the same answer using what's called this dual form solution here. Okay. So why might we want to do that? When we first look at this, it looks like the problems possibly got harder. Okay. So x, this is our usual formula here. X usually is n by p. Okay. N data points, p parameters. So this is a p by p matrix. Yeah, where p is the number of parameters or features, and the normal least squares formula inverts a p by p matrix. Okay. Whereas this formula, if x is n by p, this is an n by n matrix. So this formula, this dual form, requires us to invert an n by n matrix. So if your number of data points, n, is bigger than the number of parameters, p, you'd be better off this second form, right, the usual form. But if we're in the case where p, the number of parameters, the number of features, is bigger than n, the number of data points, okay, then you might be better with this dual form here. Okay. Now, the nice thing about this dual form is that it only contains inner products between the vectors. So again, I'm going a bit fast for you to follow this math in real time, but this matrix, x transposed from here, contains inner products between the inputs at different parts. Okay? So, this is what we called the Gram matrix before. Someone asked why it's called the Gram matrix. A Gram matrix is a matrix of inner products. Okay? So if we had this linear kernel we started with, okay, this is exactly what we had before. Okay. So why is that useful? Well, let's just think about predicting y at a new location, x prime. Okay. So y at this new location, x prime, is x prime times our estimate of beta. So if I plug my estimate of beta in here using this dual form, I get this. And this blue term is the blue term we had before, the inner product between my data locations and my test points. Okay? So, what we've got here, what we end up with, is that my prediction here is exactly the same as the Gaussian process prediction we had before. Okay? So Gaussian processes, you know, if we had this linear kernel here, Gaussian process regression is exactly ridge regression, or least squares estimation. Yeah? They're exactly the same. And we could go one step further. Instead of using this kernel here, we could alter this some way. Okay? Instead of using x, I could include x and a bunch of transformations of x. I could have a feature vector. Yeah? You've seen this when you did linear regression. So I could replace x by 1x, x squared, x cubed, cos x, sin x, e to the x, whatever I like. Okay? It doesn't change anything. It's just I've replaced this inner product by an inner product of feature vectors. Okay? And the math doesn't change. Okay? This is automatically semi-definite. It's a valid covariance function, etc. Okay? And then there's a magic that sometimes occurs if we pick the features in the right way. Okay? So just as a simple example, let's suppose we had these features. A bunch of linear and squared terms and cross terms. Okay? So what I could do when I want to compute the inner product between two different sets of features is work out this vector for x, work out this vector for z, okay? Do the inner product. Okay? Or, it turns out mathematically, with a bit of simplification, this simplifies to just this here. Okay? So instead of all these terms here, we just needed this simpler bit at the bottom. Okay? Now, you know, you've probably seen this kind of thing before, but what's going to happen is we can, in certain situations, pick phi to be an infinite set of features. Okay? And in certain cases, this reduces to a nice covariance function, a nice kernel. Okay? And the key thing is that to do regression, we don't need to explicitly compute all these features, we just need this kernel. Okay. So there's a theorem that says this is always true. Okay? The theorem says that if k is a positive semi-definite function, a covariance function, then we can always write it as the inner product between two feature vectors. Okay? We never think about it in this way, but whenever you pick a k, you are implicitly picking a set of features. Now, for most covariance functions, that set of features is infinite. Okay? And we never compute them, we never think about them, but it's a way to think about what the regression is doing underneath. Okay? So we can think about GP regression can be thought of as linear regression with a set of features, phi, instead of this covariance function, k. So just as an example, let's suppose we had a set of features that look like this. So this is kind of like an RBF regression, okay, linear regression. So for each x, I'm going to put a Gaussian hump around it. Yeah, so I've just got a bunch of these kind of Gaussian peaks around here. Okay. And my feature vector is a bunch of these Gaussian bumps in x. Now, again, I won't go through the maths, but what happens here, as you let the number of features go to infinity in the right kind of way, is that if we think about the inner product between these two feature vectors, it converges to the RBF kernel. Okay? So when you do Gaussian process regression with an RBF kernel, with this thing, yeah, with this covariance function, it's equivalent, you can think of it as if you were doing linear regression with an infinite number of these bumps. Yeah? And all of a sudden it starts to make sense why these functions are infinitely differentiable. Yeah? All these bumps are infinitely differentiable. So my resulting function is just the sum of these bumps. So obviously my samples are infinitely differentiable. Okay. So it's quite a kind of advanced idea, but it's essentially the usual kernel trick you've probably seen before in machine learning. One way to do some kind of modeling is to take your data and lift it into a higher dimensional space, do the modeling of that infinite dimensional space and project back. And this kernel trick is a way of doing it without ever thinking about that infinite dimensional space. And Gaussian processors are essentially doing the kernel trick for linear regression. Yeah? Instead of doing it in a finite dimensional, limited way, where we pick the features ourselves, we're picking a covariance function, and that's kind of non-parametrically allowing us to think about an infinite dimensional space with an infinite number of features. Okay. There's some technical jargon, okay? But just a kind of take-home message, really, here is that functions, when we think about them mathematically, live in function spaces. So continuous functions are one set of one function space. Once differentiable functions is a different space. Functions that are linear is a different space. Yeah? And often we don't think about this space, but what we're doing when we do Gaussian process modeling, when we pick a kernel, is we are picking a space of functions, a candidate set of functions. And we also don't think about that, but what we're going to do is try and validate that choice. And if you don't have a good model after a particular choice of k, you might pick a different function space. Try a different k, different kernel. Okay. And I guess the key kind of idea behind non-parametric modeling is that you're modeling some unknown function. And although the space of functions you pick might not lie in your function space you picked, if you pick a good function space, you're likely to find a candidate in there that is arbitrarily close to the true unknown function. Yeah? So, if you pick any of these kernels that we've kind of mentioned, turn, RBF, and so on, that function space is dense in a set of continuous bound functions. So in other words, any continuous function is you can find an approximation to it that's arbitrarily close within this kind of function space you've ended up with. Okay, you can read lots about those. So I'll skip this, and I think I'll conclude. So just to say, really, that GPs have become ubiquitous in StatsML. They're used all over the place now. And I think the main reason for this is that they are easy to work with compared with most and many other function spaces. Okay? It's a kind of Gaussian's a natural kind of way to think about the world. Lots of things tend to be close to Gaussian. And thirdly, we've got an ever-growing set of evidence that says they work well in applied applications, particularly applications with small amounts of data. Okay? I'll stop there. Thank you for listening. I'm aware the lunch is outside, so if there's any burning questions, I'll take them now, but otherwise, just come and find me during the afternoon, and I will happy to talk to you this afternoon. Okay? Great, thank you.